Hello, everybody. My name is Christophe Lambiel from the University of Lausanne, and I will present the result of a study about the distribution and kinematics of rock glaciers in the Southern Alps of New Zealand, a study carried out in collaboration with Gamma Remote Sensing. About the motivations, there's the fact that there are very few studies dedicated to permafrost and rock glaciers in New Zealand. And in particular, the activity rate of the rock glaciers are largely unknown. So we define two objectives. The first one is to inventory and map the rock glaciers in this part of the world, and then to estimate the activity rate of the rock glaciers with the support of Sentinel-1 INSAR data. The Southern Alps is an elongated mountain range crossing more or less all the South Island of New Zealand on around 800 kilometers. And Sattler et al. In a pioneer study evidenced quite a large number of rock glaciers in the central part of the mountain range, with the evidence of 75 active rock glaciers, 88 inactive rock glaciers, and around 220 relict ones. Worth to know also that the climate is quite diverse when crossing from northwest to southeast of the island. We are facing to very humid climate in near the main divide in Mount Cook area with around 12,000 millimeters of precipitation per year in this area. And when we go further east, the precipitation decreases quite strongly. And finally, permafrost can be found above around 1,850 meters in south exposure following the study of Sattler et al. We worked with INSAR data with about a series of about 30 Sentinel-1 images acquired between 2015 and 2019. Images, of course, acquired during the snow-free period, so the southern summer between February and April. Sentinel-1 images have a wavelength of 5.5 centimeters, and those data were projected using the NZ transfer Mercator topographic reference with an 8-meter DEM. In total, we could work with 43 Sentinel-1 SAR interferogram, 22 in the ascending mode and 21 in the descending one with time interval from 6 days to about 2 years. So the methodology that we followed was the following. We used, of course, interferograms, but also auto images, topographic maps, and of course, also we started from the Sattler et al. Inventory. And this work was performed in ArcGIS 10.7. So the starting point was this previous preliminary inventory. So we looked at all the rock glaciers inventoried by Sattler et al. But not only, we looked in fact to all different slopes and catchments and area where rock glacier, moving rock glacier, so active rock glacier, were supposed to be found. And so we mapped all the moving areas that could be detected, and we attributed to all these moving area velocity class, following the guidelines defined by the IPA action group for rock glacier inventory and kinematics. And you can see here the classes defined and a couple of polygons in this area. This job was made by 3 independent operators to lower down the subjectivity. A second step was to outline the rock glaciers, and you can see here that the outlines of the rock glacier do not correspond exactly to the moving areas. which is quite normal for this kind of study. The moving areas can go outside of the rock glacier evidence due to reason that we will discuss just after. And we can see for this example also that not all the rock glacier is moving, the lower part is not moving according to INSAR data. From this, we attributed a kinematic attribute to each corresponding rock glacier. So kinematic attribute is a semi-quantitative attribute. You can see here those velocity classes or kinematic attribute classes defined for each rock glacier and attributed to a centroid position more or less in the center of the rock glacier. Also following the guidelines from the action group rock glaciers. And the last step was the categorization of the moving rock glaciers between two categories, the active rock glaciers and this new category defined by the action group, transitional rock glaciers, which are moving very slowly with velocities below 10 centimeters per year. About the results, first thing is to say is that we had to deal with quite noisy interferograms in most of the areas, and this is an example to illustrate this fact. Here on this image, we can see a valley, angular valley with a regular valley slope facing to the east. So a valley slope made of some outcrops, but mainly also made by talus slope. And in these 24 days interferogram, we can see a noisy pattern which corresponds to this valley site, to these talus slopes. So 24 days, a noisy pattern, decorrelated signal doesn't mean movement in such landforms, but is very probably a noise. The reason of this noise is still not very clear, but it's very probably due to the humidity of the climate in this part of the world. Another example of noise here, you can see a quite clear signal in the middle of this image, which corresponds more or less to this rock glacier. This is the case for the lower part. This blue or violet purple area correspond to the rock glacier, but this pink area corresponds to the roots of the rock glacier and even the talus slope overhanging the rock glacier. These can probably not be attributed to a movement. So it's a bit strange, but it's probably a kind of noise at the roots of the rock glacier. And we can also see a number of decorated pixels surrounding the rock glacier in this talus slope as well. And those pixels can also be attributed to noise. So due to those noisy interferograms, we had to try to validate the data, and by chance we had some GNSS data for one rock glacier, a rock glacier located here on this image in the Ben Ohau range. In 2016 and the year after, we could perform GNSS survey on this rock glacier and also on this one, on this inactive one. And those velocities, the velocities showed value located below 10 to 15 centimeters per year in the upper part of the rock glacier, and mainly velocities between 2 and 7, 8 centimeters per year. And the same value can be deduced from the analysis of those two interferograms, 36 days and 360 days interferograms, with the moving areas outlined here. in the same category of 3 to 10 centimeters per year. So we could validate this kind of moving area by those terrestrial data for 2 rock glaciers in the Southern Alps. 2 examples of rock glacier evidenced here by INSAR. We can see here a signal coming from a 48 days interferogram and showing us velocities comprised between 3 to 10 centimeters per year for this rock glacier and this one as well, with the quickest part in the center, or at the roots of this rock glacier, with velocities up to 30 centimeters per year. We could also evidence a few debris-covered glaciers. We can see here the landform is a bit different, with a steep front and sharp transition between the surface and the front of the landform, compared to what we can see here, which is a very classical rock glacier that we can observe in the Southern Alps of New Zealand. And in the front of this landform, we can see a landform looking like, which looks like two kind of moraines, and we can interpret this landform as a small debris covered glacier. And there is a clear signal here at 12 days, which indicates velocities comprised between 30 and 100 centimeters per year. So velocity is higher than most of the ones that could be evidence for rock glaciers. So the global results of this study, here we are in the center part of the Central Alps with the glaciers in dark blue here and the lakes in light blue. 115 landforms were detected and mapped in 3 main regions: the Ben Ohau Range, west of Lake Pukaki, the Liebig Range here, and the Two Thumb Range. Among the 150 landforms, 7 were mapped as debris-covered glaciers, which display the highest surface movement. So more or less those red dots here. Nearly all the rock glaciers evidenced are talus connected. Only 2 or 3 are glacier or glacier forefield connected. And generally, a conclusion that we can draw from this study is already that the velocities are generally quite low. Only 26 active rock glaciers were evidenced, and 82 transitional rock glaciers, so with velocities lower than 10 centimeters per year, and as already said, 7 debris-covered glaciers. Looking at the elevations of the frontal elevation of active and transitional rock glaciers, there is only a slight difference. The active rock glaciers are in mean located about 30 meters higher than the transitional rock glaciers. And looking at the 3 different areas of the Central Alps, we can see more or less the same result for the Liebig Range and the Two Thumb Range. But in the Ben Ohau Range, the difference in elevation between active and transitional rock glacier is a bit more important. Also, we can look at the position of the rock glacier regarding the altitude, and so the mean annual air temperature. And here on this map, in blue, you can see the area where the temperature, the mean annual air temperature, is lower than 2 degrees. So what you can see here is that most of the rock glaciers are located below the +2 below the +2 degree isotherm. So the rock glaciers are located more or less in quite warm area. Only, in fact, only 9 rock glaciers are located above it's not -2, it's +2 degree isotherm. So the rock glaciers in New Zealand are located in quite warm areas. And now, if we come back to the Sattler et al. Inventory, and if we compare our result to the one of this study, we could evidence 108 active or transitional rock glaciers, whereas Sattler evidenced 163 active and inactive rock glaciers, so a number quite higher. And if we look only at the rock glaciers of Sattler, which were identified in our study, so the 108 were INSAR-detected rock glacier, about 50 of them were classified as active, 26 as inactive, and some were classified of relict, and a bit more than 20 were unmarked. So the difference between the two studies are quite important. So from this, we can drive 3 main conclusions. From the last observation, we can say that the kinematical approach, which is used in or was used in this study for inventorying rock glaciers, allows a better categorization of rock glacier activity classes, especially in this part of in this kind of mountains, with rock glacier displaying not a lot of evidence of clear activity. For instance, the front of the rock glaciers are often not very well marked, with an absence of fine-grained sediment at the front. So it's really not evident to discriminate between active and inactive landforms with only ortho images observation. So the INSAR data is really helpful to discriminate which rock glaciers are moving and which are not moving or moving very slowly. A second observation is that the number of active and transitional rock glaciers in the Southern Alps is relatively low due to the climatic first, and the topographic reasons. We could see that the temperatures at the rock glacier position are quite high, and which doesn't help rock glacier to move quite fast. And the topographic reason is illustrated by this image. This is a typical valley that we can observe in the Southern Alps, with steep valley slope with rock walls and talus slopes, and the lack of flat area at high elevation to make possible the development or the past development of rock glaciers. So the lack of fitable position for rock glaciers. And the last conclusion is that the rock glacier velocities in the Southern Alps are low, and especially comparing to other temperate mountain areas like European Alps, the rock glaciers are much slower. And the main reason is that we have relatively warm temperatures at rock glacier position. So the rock glaciers in this part of the world are for most of them, they are in a degrading state. Okay, I reached the end, so I thank you for your attention.